today we have one of the person I always look forward to learn about when it comes to binary exploitation or web exploitation. An awesome fellow contributing towards the community and now presenting here at Bayside Islamabad. Owais Mehtab, who works as a security consultant, and he'll be speaking about exploiting classic stack overflows. So, Owais, unmute yourself and do your thing.
All right. Thank you, Evad, and thank you, everybody, for organizing such a great event and letting me participate and be part of it. And so I have basically a lot to talk about, and I will be skipping a few things, and slides are there if you want to follow along. So the topic I'm going to discuss about, basically demonstrate about, is basically about exploiting classic stack based buffer overflows, and I will just skip a few slides like the boring one about me or who am I. I'm just going to skip that all along, and then we will just hop on towards the agenda. And what's the agenda for today? So basically we will understand what is buffer overflow, and why is it caused, what could happen if a buffer overflow occurs, why it occurs, and then we will quickly look into the prerequisites for understanding such exploits, like understanding how the assembly works, what are sections, how the instruction works, things like these. So just a little bit about stack-based buffer overflow. Basically, what it is when you start a program, and then let's say the program expects some input from the user, and we provide overly long string or some sort of data that program cannot properly handle, the program would eventually crash, and then that depending upon the conditions, and it can result in denial of service, it can result in arbitrary code execution and things like these. So we will quickly look into some of the assembly things, and develop a basic understanding of how things are working behind. So basically there are multiple sections for a program, and then we are going to look into the data section, text sections, VSS, RSRC, relog. So basically the data section is used for initializing data or constraint. This does not change over the time. And the BSS section is used for declaring variables for a program. The text section is where the actual assembly level code resides. We will look into some programs, how they look in C, and what they look like when they get compiled into a Windows binary. And we are just going to talk about a little bit about the registers, because these are a few important things to know about before diving into a Stack Overflow. So here we are just going to focus on the general purpose registers. And basically there are like multiple types of registers, general purpose registers and segment registers. So general purpose registers are EAX, ECX, EDX, and EBX, ESP, EBP, ESI, EDI, and whatnot. So EAX and EDX basically are used for arithmetic operation, and EX usually holds your written value as well. For example, if a function is called and it is performing some action and then returning some value, EX is the register that is going to hold that value. Similarly, ECX is basically used for loop-based operations or for counting. EBX is basically a pointer to the data, and EBP is basically base pointer. It is a frame base pointer, and then ESP is also a stack stack pointer, which basically points on to the top of a stack. So a few things to remember about EBB plus something is always argument for the function, and EBB minus something whenever we see is usually the variable, the local variable of the function. So these are the registers we usually see in like 64-bit and 32-bit and 8 bits processor. So for now, we have like, if we have a 64-bit architecture, or if we have a 64-bit system, these are RAX, RCX, RTX. Similarly, we have 32-bit registers, that is EX, and this is the same register, but it is referred to as EX, ECX, and EDX. Similarly, if we want just to access the first 16 bits of the register, we can use AX. Similarly, if you just want to access the first 4 bits of the register of EAX, we can use AL. And similarly, if you want to access specific bits of the register, like from 4th to 7th bits, or 4th to 8 bits, we can use AH, and similarly for other registers as well. But not all of the registers can be accessed in chunks. Only the mentioned one can be accessed in such a way. For example, if you notice here, EDI can only be accessed by DI and DIL, but not DIH or something else. So a few things to keep in mind when looking at the assembly instructions. So basically, if you look here, the first instruction is basically moving the value 123 into register EAX. The next instruction is very similar, but here's a catch, and basically it will move whatever, it will first look for the value in EAX, go to that memory address, and then copy 123 on that memory address. For example, EAX contains, in this case, and on the second instruction, if the value of EAX is 1000, what the program will do is go to the memory address 1000 and then copy the value 123 on address 1000. Similarly, add instruction here. So what it will do is, whatever the value is in EAX, it will add 1 in it and save the result in EAX as well. So the next instruction here we have is add EAX and then square brackets 1, 2, 3, 4, 5, 6. So what it will do is basically go to the instruction 1, 2, 3, 4, 5. I'm sorry, I slipped. So it will go to the address 1, 2, 3, 4, 5, 6, and then pick whatever value is there, and then add that value into the value of EAX. Similarly, the last instruction we are going to look at is move EAX and then bracket square brackets 1, 2, 3, 4, 5, 6. What it will do is go to the address 1, 2, 3, 4, 5, 6, and then copy the value whatever is present on the address 1, 2, 3, 4, 5, 6, and copy that to EAX. All right, so the program we are going to look at are basically using standard CDACL calling convention, and then we will, if you have any queries about calling conventions, we can you can drop down through Discord channel or the YouTube chat or whatever you find easy to. So I'm gonna skip it, and then let's look at this diagram. So basically, let's say there is a function and that is calling another function. What it will do is it will basically save return address, EBP, and then here it is basically pushing the arguments on the stack, and then when the next function is being called, so it would push the EBP and basically the base frame pointer. So once that is pushed, it will start virtually a new stack for the function that has been called, and then once the function exits, it will pop the value of EBP that is saved here back into the EBP, and then clear up the stack, and then once that value has been popped out, it will return to the address. So basically, whenever function returns, it is basically something like leave and then followed by a return instruction. So basically, leaves does the magic of like clearing up the stack that is used by the current function that was called when exiting. So we will look at another diagram to elaborate things a little further. So this is, let's say, this is the main function, and it has some variables and then some arguments being pushed, and then the sum function is being called, and finally it is returning value 0. So basically, here, whatever is represented in the red is the stack of the main function, and whatever is represented here in sort of yellow color is representing the stack of the function sum. So again, remember, EBP minus something is variable for this function, and then EBP plus something is always the arguments for this the function that has been called. So we will look into the code, and I'm just going to minimize the slides, and then because I strongly believe if I'm just going to narrate all the slides, it won't make much sense rather than giving a live demo. Everything is documented in the slides step by step, and we will just do it live here instead of like going through the slides. So if you have any queries, questions, please feel free to shoot on the YouTube chat box or the Discord server, and I would be happy to answer to the best of my knowledge. And let's dig into the first program, sum.cpp. So here we are basically defining some headers and whatnot. Then we are describing a function that is returning a value of integer, and it is expecting two integer values, and then the integer x and integer y are basically the arguments, and then we have here another local variable being initialized, not being initialized, just defined, and then later on we are storing the sum of the two arguments in that variable, and then calling three printfs here, and then returning the value z, variable, whatever the value is stored in variable z. And here we have the main function. The program always starts from the main function. Keep that in mind. So here we are initializing two variables, I and j as 0, and then assigning the value 10 and 15 respectively, then initializing another variable k as 0, and then calling a function sum, and then whatever it will return, we are going to store that value in the variable k, and then finally printing it out. So this is how the program looks like in C. Finally, before switching to IDA, to look into how it looks like at the assembly level, I would like to point out that this main function is also returning value, integer value, and that is 0. So I would just quickly open it in IDA and then look for the main function. So this is basically what the main function looks like. This is where the stack is being set up for the main function, and here we are initializing the variables to 0, then assigning the values 10 and 15 respectively. Then we are doing some more variable initialization, and then we are moving the value for one of the variables into EAX, and then pushing onto the stack the value of EAX, and then moving another value from the stack into EAX, and then pushing that somewhere, and then finally calling the function. So probably it would not make sense right now, but if we look at it through a debugger, it would make much more sense. So here our IDA has renamed the function, but in the comments we can see this is indeed the sum function, and we will just quickly go back here and just look at the addresses. So this is where the main function starts, and then we will set a breakpoint, a few breakpoints, and then we will continue the execution from here in immunity debugger. So basically, this is a debugger to debug a program. I will just quickly load the program using by pressing F3, and I would load the executable foo. So before like looking into these areas, we need to set up a few breakpoint. I have already configured the breakpoint. So how do we configure the breakpoint? We just need to type pp and whatever the address we need to break it. So the debugger, as soon as it reaches that specific address, it would pause the execution. So I would just go and look the addresses where I've put the breakpoint. So I can press Alt plus B, and here are the list of the addresses that we are going to pause on. So I would just quickly go back to this assembly view. This is basically our debugger. This is the disassembly view. This is the registers view. This is the stack view, and here we have the hex dump, that is basically the memory dump. So I would usually program stops pause at the entry point. We will let the execution continue, and now we can see that we are indeed at the first instruction. Sorry, I loaded wrong program. So I would just quickly exit my debugger and Unity 3 sum. So I would just repeat the same steps. I've already configured the breakpoint. So if we look here, this is exactly the same thing as we saw in IDA here. The push EBP, move ESP, and something, and then followed by a call, and these are the instructions. So if you look here, we can see all of the instructions are there. We are paused currently at this instruction. As we can see, EIP basically contains the address of the next instruction being executed. In this case, it is calling a function. So I will just quickly step over. So basically, there are multiple types of stepping. Stepping into the means that execute one instruction. Step over means, for example, if a function is being called. So what the debugger will do is rather than going into the taking us into the function, it would execute that entire function and then return the control to us once that execution is done. So this can be done by pressing F8 or from this menu and then step over. And so I would just press F8, and we would see that we are indeed here. So here we have this stack. Currently it is pointing to this address. So if we look here, what this instruction will do is initialize the variable value to 0, as we just saw in the C code. These variables are being initialized, and then we will just quickly look into immunity and see what it is doing. So notice here, there is only one 0 on this address. So if you do the math, FE80 plus 1C is FE9C. That is this address, and this contains right now the value 21. If we step into this instruction, so this address now contains 0. So similarly, FE8 plus 18 would be this address, and if we step over and see now this value, this address also contains 0. So now the second, these two instructions are basically assigning the new values 10 and 15 respectively. Hex equivalent of 10 is 0A, and hex equivalent of 15 is basically 0F. So I would just quickly step over and notice these values have indeed been pushed. And then now this is where our third variable is being initialized. And then, as you can see here, and then now we are moving whatever the value of variable I is being moved to this register. Notice the value EX has 1, it will now contain variable F. So it is moving basically the second parameter and then pushing it on the stack. If you look ESP plus 4, so basically this would be the address. So here we can see EX has indeed been pushed, and now we are preparing for the first parameter, because the CDACL calling convention basically takes the parameter from right to left. So it will push the rightmost parameter on the stack, then the next parameter, and then the next parameter. In our case, the function sum was only accepting 2 parameters, so it is going to push the next parameter or the first parameter on top of a stack, that is this address. So if you step over, we can see quickly that indeed these 2 values have been pushed on top of a stack, that is and now we are calling the function sum. So if we step into this function that is in actually sum, what will happen at the background is, if we notice here 00401599, that will be pushed here, and then EBP will be saved when we are actually into the sum function. So what we will do is quickly step into it and notice 401599 being pushed here. So here we are, and now it is in this function. The sum function is basically setting up its own stack. So it is saving the EBP as we already discussed. Now it's setting up its own stack and now adding some values. So we will notice that this value will be moved down quickly. As we can see, somewhere here, it has been pushed down, and now we are looking at EBP plus something moving into the register EDX and EAX. So it is referring to EBP plus something and EBP plus something. Remember, EBP plus something is referred to as the function argument. Whenever we see EBP plus something, it is referring to the function's argument. So if we step into, so look at the value of EDX. Indeed, it is containing the value of the first parameter, and if we step in again, EAX contains the value of the second parameter, that is 15 and 10. EDX contains first parameter and EAX contains second parameter. So at this stage, we are just basically performing add. So it will store the result in EAX, and this is what it looks like in hex. And then if we look here, the function is still not showing anything, displaying any kind of output. So basically, we will just continue execution till here, right before the call to printf, and then we can see some values have again been pushed on top of a stack before calling the function printf. And we can see in this case, printf is expecting 2 arguments. The second argument is basically the format is specified. The first argument is basically the address, which contains the string argument 1. And if we go at this address in the memory dump, it indeed contains the string argument number 1. So we will just quickly step over and look at the program. So it will quickly say that argument 1 is this and whatnot. And similarly, what we are doing here is again calling printf, and I would just configure this breakpoint here and then pause the execution again here, and it would basically, it is pushing the address of this instruction, and then pushing as the second argument is being pushed as basically whatever we passed to the function, and that is value 15. And then if we step over on that function again by pressing F8, we can see indeed that the second value, the second argument value has indeed been printed. So we will continue the execution up to this point by pressing F9, and then step over. And we can see the sum of the 2 arguments is 25, which exactly we are here in the code, and finally we are returning. So remember, I told you about EX contains the return value. Notice EX contains 1C right now. If I just step in, and now EX contains the value 19, that is the equivalent of 25 in decimal. And basically now look at the leaf, and remember the 599 value somewhere pushed here. If we just step one more time, so yes, this is the address of the instruction we saved on the stack before calling the sum function. And then basically now we are just returning to the address, and then whatever is on the top of the stack, it will return to that address. So if we press F7 again, we are indeed back into our dear main function. So I would just quickly go through printf again, or let's we are here. So ex is being pushed to ESP plus 14. This time the compiler has done some tricks and try to fool us around, but basically if you look here, it is basically referring to the variable k address. So if we notice here, ESP plus 14, it's probably this address. And then if you step over, it is basically containing hex value 19 that is equivalent to 25. And then due to the lack of optimization, it is moving back and forth the same value over and over again. And that is moving EX to sorry, this is basically, these two instructions are basically preparing for the arguments of the printf function again. So it is pushing the second argument, and this is pushing the string value. So if you look at the code here, this is the address of this string would be pushed, and then the format specifier or the address of the variable k will be pushed. So I would just quickly step over, and we can see here, and we are here, and if we look at the program here, something is not working, so I'll just quickly restart the program, and I would just step over a few things. Here, and I will just quickly go over this function that is basically printing this line. So you can see the value returned from the function is this, and blah blah blah. So now the main function is returning value 0 and exiting. So if we step over, ex contains 0 and leaving, and then if you follow along a little bit more, it is basically calling exit to exit the program. So if we here, and we can see the process has indeed been terminated. So now that we know how the function is being called and how it looks like when the parameters are pushed for a specific function, we will look at another example. Okay, so we will look at another piece of code, that is foo.cpp. So it is basically, we are defining a function foo bar that is not taking any input nor returning any value, just printing a value. You have reached a secret function and then calling and then some another function. Excuse me. But remember, whenever we start a program, it always executes main function, and we don't see any call to foo bar in the main function, so it won't this function would not get executed at all. So let's look into the main function. Here we are defining character array of 32 bytes, another character array of 16 bytes, and then we are printing something, and then we are taking input using fgets, then we are echoing it back to the user, and we are saving the user input in this buffer1, and then echoing it back, and then we are printing this string, and then using a scanf to take the second input, and then echoing it back, and then returning 0. So we will quickly look at how it looks like in IDA, probably. Yep. So this is the main function. As we can see, there is no call to foo bar, and then this is how it looks like in the graph view, and it looks like how it looks like in the text view. So we are going to set up a few breakpoints, especially on this function, this address, and then we also would like to notice the address of foo bar, but not here. What I will do is load this thing in Unity, and let's function foo. All right, so I would like to point out this address 401 for FA, as this will be referenced later on, and as we can see, the function foo bar is indeed here, and here we have the main function. If if we want to confirm, this is taking the first input, this is taking the second input, which confirms that this is our main function. So I would just let the execution run and until we hit the breakpoint. So we are on the main function. Now, if we step over quickly a few things, so basically we are pushing on top of a stack this address and then printing it out. So if we step over and we can see printf has been called, and then program is basically saying input number 1, and then we are setting up some parameters for this function. So what I will do is I will quickly reach to this function. Before reaching to that this function, few parameters have been configured here. If we look at the first parameter, so we need to follow this one in dump. This address contains some garbage and data, and this is basically specifying the size, the 32 bytes, and then this is something else, and then I would just let the execution run. And if we type maybe cd this, and then we can see indeed this address now contains what ABCDEFGH, and this is pretty much it. And the function return, and now we are configuring some parameters for printf again to print this string, and then I will just step over quickly, and I won't go into the details of this printf function again, and then we are just basically printing and pushing the address of input number 2, and then calling printf, and here we can see this is our input has whatever the user provided has already been echoed out, and then another call to printf has been made where I stopped, which says input number 2. So basically, the previous printf function was just echoing out whatever the input the user provided. Now we are setting up parameters again for the scanf function here, and I would just quickly where is my execution? My execution currently paused here. So scanf function is being called. So if we look at the address of the scanf, let's go to the expression. No, sorry. Follow address in dump. It's probably this or this. I don't recall exactly. I think this was the so I will just maybe A, B, B, C, C, and D, D. And sorry, this was the address. So if we go to the address, it indeed contains our string. So now this is where the program is exiting the function sum. So I would quickly go over it, and then it is finally printing one more print that we mentioned, that is whatever the second input of the user provided to the program, and then moving value 0, and then returning. So notice before calling that function, we saved the return address, and then we will probably return back somewhere here. And then if we press F8, sorry, I clicked on the wrong address. So this was the address which we saved, and we are returning to this address, and we can the program is exiting right now. So let's restart the program, and if you are following along with the slides, so we are basically on slide number 45. So, this is where the we discussed about the program and whatnot, and then so the program gracefully exited, and we will restart the program. And then what if we basically provide more than 32 bytes to the first input? What will happen? So let's figure out, and let's send 64 A's instead of like 32 A's to the program. And then let's continue the execution. We will continue at fgets, and I would like to point out this address FEAC. Where did it go? The program returned to this address. If you remember, keep this address at 0061 FEAC. Right now it contains some return address, and if you provide overly long string and press enter, so this still contains something, but if we gradually continue F9 to this point, it won't ask for the second scanf. And I would probably pause here, and if we look here, now it contains 4141. Now we have basically overwritten return address of one of the function that was being called. So if we let the execution continue, the program will not ask for the second input, rather it would just go lost. And then finally we have EIP containing 4141, and then indeed the program did not ask for the second input, and instead it just overflowed into the second input, whatever we provided in the first input. This is where things get interesting. So now we can see that we can control EIP, and if you remember, EIP contains the address of instruction that is being executed. If we can control EIP, we can control the flow of the program. So we will quickly restart it and remember the address of the foobar function. This is the address, and if we somehow manage to hop over here, the program will continue the execution from there and then go to this point. But we have a few challenges. That is, this program is being loaded it starts in an address that starts from 00. 00 is basically a string terminator or the null byte. Null byte basically terminates the string. So what can we do in this case? We can get around this problem by partially overwriting the EIP. As you can see, the EIP also already contains 00 in its most significant byte, and we just need to partially overwrite the EIP instead of like completely overwriting the EIP. So we will just overwrite 3 bytes in EIP. Okay. With that in mind, we have to figure out how much amount of data is exactly required to control EIP. So for that, we have something called unitary analysis. What I will do is instead of sending 64 bytes of A, I will send 32 bytes of A followed by 32 bytes of B, and then see if the EIP contains Bs. So I would just split the B into 8 bytes of B and 8 bytes of C, and then continue the process further until and eventually I will figure out how much bytes are exactly required. So I would just quickly go through this function and then just provide a demonstration for this one, and see the EIP contains B. So we will continue splitting it up to this point. For the sake of time, I'm just going to copy the last string and then just providing as input. So if we provide this one and continue the execution by pressing F9, we can see indeed that it contains 45454444. So that means we need exactly 59 bytes of A's or exactly 59 bytes. So in order to confirm our theory, we can check this thing. That this string contains basically 59 A's and then followed by 3 D's. So it should, if we provide this one, EIP should contain 00444444. And let's restart the program by pressing Control F2 and pressing F9 a few times again and providing the input, and there we go. And then let's see. Indeed, it contains 004444. Now that we know how to precisely control EIP, remember that address. Let's look into the exploit code. What is this exploit code doing? It is basically creating a file label.txt, and then we are concatenating the address. But due to the Indianness that the Intel CPU follows, we have to flip the bytes, and then we have to write them in a reverse order. So 004014 FA is written as FA1440. So I would just quickly demonstrate this one to trigger that function foobar, and foo.py. So it is basically creating table.txt, and if we pipe that output in foo.exe, C, it should trigger that foobar function that was never called. C, and we can clearly see that we have indeed been successful in triggering a function that was not there. So this demonstrates the power of stack-based buffer overflow, but this is not something very interesting. Rather, I would like to show something more interesting. And right now we are at slide number 74. So now that we have covered pretty much a lot of information about buffer flows, I would just quickly demonstrate exploit against a real-world application. And basically, what I'm going to do is start with the crash, analyze the crash, and then from there onwards, we will follow the same process. Instead of calling a predefined function that was part of code, we will try to introduce our code and then try to trigger a calculator or try to execute a bind shell. So this is pretty much in the nutshell. What we are going to do is triggering the crash, analyzing the crash, follow which registers points to our control data, and figure out how much bytes we need to control the EIP, then find the address for the shellcode. Find the space for the shellcode that we need to place or the code we want to execute. Then find out what are the bad characters. Bad characters is basically we will talk about it when we reach that point, and then find a relevant jump to that to our controlled area or the register that is pointing to our controlled buffer, and then we will place in some knobs and then followed by some shellcode, and voila, that's all pretty much all we need to make a working exploit. So let's start. So this, I'm going to start with the first POC code. This is basically creating an evil M3U file, appending 27,000 A's inside it, and then finally closing it. So I would quickly go and create one, and we can see evil M3U has been created. So I would load our vulnerable application inside immunity debugger, and we will continue the execution. And if we look here at the desktop, evil M3U, and load it here, indeed we can see EIP contains 414141, and ESP basically points to the address that also contains our data. So now that we know that we can control EIP, we can again follow the binary tree analysis approach we just followed for the previous program. And let's restart the program and let's look at the POC number 2. So what we will do is we will split the 27,000 of A's into 20,000 of A's, and then 7,000 of B's, and then see what the EIP contains. So I would quickly delete this POC file, and I would just double click on POC2 and let the execution run again, and let's see. Okay, now that EIP contains 424242 or the B's here, that means that as the crash occurred somewhere between 20,001 and 27,000 byte. So what we will do is instead of continuing the binary tree analysis, we would send a unique 7,000 bytes unique string that and figure out where the crash exactly occurred. So we can use a script provided by Metasploit framework to create such a long string, and basically it's pattern create and then followed by the length. So while it is creating that string, I would just restart the program again by pressing Ctrl F2 and clicking on yes, and pressing F9 to let it run and do whatever it wants for the time being before we crash it again. And here we have the unique string generated. So we would simply copy paste it. So the new POC code would look like something like this one. We will again create a evil M3 file followed by and it is appending. Yeah, sure. So it is appending 20,000 of A's, and then followed by 7,000 bytes of string, and then this is what we are going to create another evil M3 file, and we will analyze the crash again. And now the EIP contains this value. We will feed this value to pattern underscore offset, and we will see that it would mention that this would mention basically 6,081 bytes. And let's wait. In the meanwhile, I will restart the program, and as you can see, exact match is this 6,081. So that means the exact crash occurred at 26,081 bytes. So our POC code 4 would look like something like this, and we will append 2681 bytes of A and then followed by 4 bytes of B. So if everything is, if our calculations are indeed correct, so we would just generate a new POC and let the program run again. And EIP indeed should contain our B's. Yes, and an ESP contains our C's. So now we have to figure out the shell space. We have already figured out the exact amount of bytes to control the EIP. We will note this address and then follow the ESP in dump, and we will start looking where the C stops. So basically it stops somewhere here. And if we subtract this address from this address, it would result in almost value 388 or something. So 1009C minus FFCC4 3D8. That means almost we have 984 bytes, and we have 984 bytes of shellcode space. The next thing we have to figure out is the bad characters. So in order to figure out the bad character, what we would do is create another evil M3 file, and then send, instead of sending C's, we will send a byte array of containing values from 01 to 0xFF.
Yes, we got a lot of questions as well as feedback from people out there. So I think if we can just wind it up, we're getting late.
Yes,
with
I'm
another.
just quickly winding it up to the point where
Thank you
we
so
look
much.
at the shell
Thank you
code.
so much. Thank you so much.
I really appreciate for giving me a little bit of extra time, and like a lot more than a little bit of extra time. So just let me continue with this one, and then we had POC number 5 here, and then we will look at the bad characters here. So the thing what we would do is follow this in dump again, and if you follow ESP in dump, we can see that it indeed contains these values and these values. So that probably means 09 is the culprit that is basically breaking our shellcode, because we could not see anything other than after 08. So we will just quickly remove that character and then continue the execution. Similarly, we will remove 0A, because usually it is also considered as a bad character. So we will just restart the application here and press F9 again, delete previous file and generate the POC. Okay, we have this file generated here, and we see here, EIP contains this value, and ESP now contains everything we have, nothing breaks here. And the next thing we need to is to figure out jump to our register ESP, jump -r ESP. We are going to quickly use Mona to find this address, and then we will look at the log window by pressing Alt L, and then this is the instruction that I'm going to use. So the next POC would look something like this. It contains our shellcode, it contains our jump to ESP, and followed by some knobs, because shellcode sometimes needs a space to decode itself. And as you can see here, ESP basically is pointing in the middle of our byte array, not exactly where it is starting. So we also need the knobs for that thing. So we will just quickly generate a new POC. And set a breakpoint BP 1001 B058. This is where our jump to ESP contains. So let the program run, set the breakpoint again, and we are going to use this POC9 to generate this thing if everything works fine. So we should hit our breakpoint. Indeed, we hit our breakpoint if we press F7, F7 again, and we are landing here on our knobs. And if we continue the execution, it should pop the calculator. Indeed, it did. So that's pretty much it that I have to share with you guys. And thank you again, Abad, for giving me the extra time I needed. And that's all I have to share.